So this is just a really quick video on centripetal acceleration and to a lesser extent centripetal force. So to keep an object moving in a circular path, a net inwards force must be present. This force acts perpendicularly to the direction of motion and is known as the centripetal force. Now we'll get onto why it's perpendicularly to the direction of motion in the next video where we cover the proof. Because a force acts inwards and F is equal to ma, which we can actually sort of more so justify saying F is proportional to A, so they actually act along the same line of action, we must conclude that there's a centripetal acceleration, or centripetal force, I should say. So there's a centripetal force also directed towards the center of rotation, which is perpendicular to the direction of motion. So in terms of vector form, if this is our center and this is our object P, if we're going to have two vectors, one of which will be in yellow, so this will be our acceleration vector that's acting inwards, but we'll also have a force vector acting inwards, which is a scalar, the mass, times by the centripetal acceleration. So I should put all arrows on top of these. That's not the same color, but however. So, despite this, it may appear that an object is not accelerating while in circular motion. We're going to be dealing so far with uniform acceleration, or well, uniform circular motion, which means that there's no, the object isn't speeding up. But actually, even though the magnitude of the acceleration is constant in uniform circular motion, the direction varies constantly throughout the motion. So even here, the force is directed here, but if the particle were over here in this same arc, we'd actually get a force acting inwards here. So that's F1, so this could be F2, is mass by acceleration. So the direction of the force changes, but the magnitude of the force doesn't.